this. So if functions have an inverse, or we say that they're invertible, they are reversible, they have characteristics, operations that we can reverse. The inverses are functions, which means they have to be a one-to-one function. So not only do they pass the vertical line test, but they also pass a horizontal line test, so that each x, y value is unique, and none of the x's repeat, and none of the y values repeat. All right, moving on to some examples. So determine if the following functions are one-to-one. We're going to figure that out two ways. We're going to do it both algebraically or analytically, and also graphically. Okay, so let's take the function f of x equals 1 over x plus 2. I think we talked about the reciprocal function back in section 1.2. Wasn't that one of our toolkit functions? The reciprocal function. So just a quick reminder of what our reciprocal function looks like. If we have y equals 1 over x, it's got asymptotes at 0, and it is the top right and bottom left, or quadrant 1 and 3. Okay, so what would it be? Let's practice what we learned in section 1.3. What happens to our graph if we have an x plus 2 inside the fraction? What direction is that going to move in? Left, right, up, or down? It is going to go to the left because it's an inside value. I mean, there's not parentheses, but it's still inside the fraction. So when it's inside the actual function, it's going to go left or right. It goes the opposite direction. So this particular graph would be going to the left too. So our asymptote would move to the left too, but we still would have the same basic shape happening here. Now I haven't drawn this very carefully. It almost looks like my curves are curving back in on themselves because I didn't draw it very well. But this is a function, yeah, for sure. It passes the vertical line test. Does it also pass the horizontal? I can't see. It passes vertical. Does it pass horizontal? Yes, even though I've drawn it improperly, so it doesn't really look like it does. It does. So our graph shows us that it does pass both the vertical line test as well as, and I said the wrong thing again, the horizontal line test as well as the vertical line test. So this is a one-to-one function. Oops, many steps back. So graphically, yes, we can see that it's a one-to-one function. How do we check that algebraically? Well, what we're going to do is see if the rule we learned on the previous page actually works. So what that said, if you remember, it said f of c is equal to f of d. If that's true, then c equals d. Remember that? So let's go ahead and do this process with our function. So we're going to have 1 over c plus 2 equals 1 over d plus 2. We're going to cross multiply. So we have d plus 2 equals c plus 2. And then if we take 2 away from each side, we're left with d equaling c or c equals d, whichever, right? So algebraically, that works as well. Okay, look at this second one. This second problem is a parabola, right? Because it's x squared, so it's quadratic. Right now, it's in what we call standard form. So that's a little bit different than vertex form because it's written out like it's all multiplied out. But it's not easy to graph in that form. We will learn about those extensively next week in section 2.1. But for now, we're just going to see how much we remember about this. Do you guys remember that you could factor this? What will those factors be? Actually, does it factor? It doesn't factor, does it? Factors of 4 that add up to -2? It doesn't factor. I was thinking it does. We would have to do what's called completing the square on this one. Do you guys remember completing the square? That sound familiar? Is that something you ever learned? Does the term completing the square sound familiar? Okay, so I don't expect you to remember this right this second. This is more important. It's going to be more important in chapter 5. But I don't think it hurts us to see things more than once. So to complete the square, we need to add the number that will make this a perfect square trinomial. So what that means is we take a number and add it to itself to get the -2 in the middle. And then that number times itself is going to be the last number on its little factor. So what number would add to itself to get -2 in the middle? -1 twice, right? So that means we would need to go -1 times -1 to get that number. So -1 times -1 is +1. But what is the actual number that's there? The actual number in our problem is a 4. So if we only have a 1, we're missing 3. So I'm just going to write that 3 separately. So now this will factor into x minus 1 squared. And now we have that in a vertex form that's easier to graph. What will the transformations be for this? Yeah, perfect. Right 1 up 3. And of course, it's one of our toolkit functions, so we know it is a parabola. So our graph would look something like this. Now, I was very precise about my graph. I don't know if I necessarily needed to be precise graphing that, because in a nutshell, it's a parabola. Is it going to be 1-to-1? No, a parabola is not a 1-to-1 function because it's going to fail the horizontal line test. Not 1-to-1 because it fails the horizontal line test. Okay. Now you can do this problem algebraically as well, and it's really ugly. I don't know if we really care about going through it, but when you get to the end of the problem, you end up discovering that C equals D plus 2. Just by plugging it in like we did before, but there's a lot of multiplying and factoring involved, and it's really ugly, and I don't want to spend that much time and make your brains hurt right now. So just know that the graph proves it, but also if you were to work it through algebraically, it doesn't work out. Okay, so we're just going to say no. Okay, suppose functions f and g are inverses of each other. Okay, then these specific rules apply. So the range of f is the domain of G. And conversely, the domain of f is the range of G. They just trade domain and range. All right, that was one I didn't really fit in there very well. The second rule is f of a equals b if and only if g of b equals a. Let's make sense of that. So this means we're pointing in an x value. We're getting out a certain y value. So if G is the inverse, the domain and range switch. So now instead of plugging in A, we're plugging in B, and we're getting out A. So for this problem, A is part of our domain and B is part of our range. But then for the inverse, those two things switch. B is now the domain of that function, and A is the range. Right? And then 3. Here's the third item of importance. A, B is on the graph of function f if and only if. When I say if and only if, that means it has to go both directions. B, comma A is Okay, so all we're saying here is that our function and its inverse, the domain and range trade. The x's and the y values swap. And we can use that to help us find inverses. We can just trade the x's and y's, and that will allow us to find inverses, which we're going to see in the next few examples.